So the next part of the talk is a little part about the obstacle problem. Okay, so there are some specific results that you can get if you are dealing with an obstacle problem. So the obstacle problem, I remind you, is this one, and you have just two possibilities, two controls. So the control set here, we are in the situation where A, the control A, is just a 0 or 1. And okay, so you can write, so we write exactly the same algorithm, but in this specific case, because you have just two controls, when you look at the minimum, if, for example, at a certain, for xk, if you see that for this component, the two values are equivalent, then you choose always the control alpha e equal to 0. You give some advantage to this equation. Do you remember the notations or not? Let me maybe write down what we are talking about. So we have alpha 0, A0 is equal to Q, and B0 is equal to B, A1 is equal to the identity, and B1 is equal to J. And we are just minimizing, solving the equation yes, A1 x minus B1 equal to 0. This is what we are solving. So at each step, step K, first what you do is you solve the problem with the A alpha K x K plus B alpha K is equal to 0. It means that what you do is you mix so you take some rows from this line, A0, and you take some other lines from this, some other rows from A1. You are mixing, depending on your strategy. For each line, you choose the first or the second equation, okay? And then you may have on alpha some components are equal to 0, which means that you have the row from this line, or some components are equal to 1, which means that you have rows from this equation. That's clear for everybody? Okay. So here this strategy again, I remind you that this is a function for each, well, a vector. And for each component, you may have a value 0 or 1. So you solve this equation at set K with this specific strategy. And then you take alpha K plus 1, I. It's equal to the minimum. You fix xk now. And you take the minimum of A0 x minus B0. K, A1 x minus B1. You look at the argmin, component by component. So this is the component I, and this is also the component I. Okay? So this is how you do the computation. So what I'm saying here is that if you, for I, if these two quantities are equivalent, then you can choose either 0 or 1, but choose 0. Just in this situation, we always make the decision to take 0. Is this clear? Okay, so this is exactly the Howard algorithm, but with a specific choice. When the two terms are equal, then in this minimization, you always keep alpha I is equal to 0. Actually, the theorem says that either choices would be fine. You can choose one or another. You are fine. But if you choose this one, then you have some nice properties. The first one is that if you always if you always do this choice, then your Howard algorithm can be also reinterpreted like a primal dual active algorithm. I don't know. You are expert in optimization. I don't know if you know this specific algorithm or not. So primal dual active algorithm. Okay, if you don't know it, it's fine. But I always find interesting to make links in mathematics. It's interesting. It gives another perspective, and you can understand things differently. So the Howard algorithm is equivalent to this one, and there is quite a huge literature on this primal dual active set algorithm, even for infinite dimensional spaces. And also the other information you get is that Howard algorithm, by making this choice, would always converge at almost n iteration. Do you remember the first theorem? I told you that if you have a finite number of actions, then you have a finite maximum number of iterations. Do you remember this bound? Yes, it was cardinal A 2 to n. Yes, thank you. So it was cardinal A power n. So it means that in my case, it would be 2 power n. Okay? But by making this specific choice, you gain a lot. From 2 power n, you have just n iterations. I'm very careful about that, because usually we apply the algorithm to solve some huge problems, so there is no room to waste time computing something. If we can gain some CPU time, it's always interesting. And this is a situation where you can go from 2 power n to n iterations. Why is it working here? Because in this specific case, we do have more than just the convergence. So what we have is also some properties. By making always this choice of alpha I equal to 0 in case of equality, you have a decreasing set of policies. And in this situation, you have also convergence of policy. But this is very specific. This is just an obstacle problem. Okay? But it is nice. And to prove that this is a decreasing, well, we have the same kind of arguments that we have seen before. So you can prove that each time you improve a little bit, little by little, at least you improve at one component, you will improve your strategy. So at most, you have n steps to improve for each node. Okay, just to see this in an example, and the example I am dealing with is coming also from stochastic optimal control, and it's called American options. So this is the situation where we are looking at this value function now u. The value function is u, is solution to this PDE, partial differential equation. Again, this notation stands for the derivative with respect to time. This is the derivative with respect to s. the second derivative, this is the first derivative, it's quite similar to what we had earlier, apart that now we have this obstacle, okay? So we are optimizing, but at a certain point, if we see that the price will be over a certain amount, we stop the game. So American options is so it's a known problem, and the value function can be described by this equation. So this is called in the literature, it's a very specific example for what we will see in stochastic control problem called the exit time problems. So we do have also this some information on the boundary for this kind of problems, and we have an information at time 0 as earlier. But here for the American options, the payoff is not an utility function. We are dealing with calls or strikes or puts, and the payoff is a function in this form. So the maximum of k minus s and 0. K is a fixed, it's called the strike. Okay. Now you can just trust me that it is linked to a stochastic control problem. So, but what can we do with this? We also are interested in the discretization. So we discretize the time derivative, the second derivative, and the first derivative. So the notations are here, but it's basically as before. The second order, you have simple terms for the first and second order derivatives. What you should note here is that for each time, we have a nonlinear system, and we have ns points. So this vector u at time n plus 1 has ns components. So according to my theorem that I showed 3 slides earlier, the conversion should be for each time step. For each time step, for each n, I should have a convergence in ns steps, okay? Ns iterations. And okay, here again we can write all the matrices. We can show that they are monotone and we are in the good sitting. Now, yeah, this is the matrices. They are they have good properties. And let us just look now to what we get numerically. So this is a very specific situation where at each step we improve a little by little. So this is what we have. The black line was our first payoff. This is the function phi. Remember, it's the maximum of k minus phi of s is the maximum of k minus s and 0. So this black function. And then at each iteration, at each time step, we improve. So if in the algorithm, when we want to compute un plus 1, if we compute by starting from un, then we gain a lot. The total number of iterations during the whole time interval from 0 to nt is not nt times ns, it's ns. Okay? For this specific equations, we can prove that the solution has some properties that let us get this bound not only for each time step, but for the whole interval. Okay, that's it. This is what I wanted to mention about this problem. Any question or comment or complaint? Or
Just a curiosity, there is any interest in
Of course. People, they want to have a very efficient and very precise results. In some situations, you want just to have a rough bound. But in other situations, people, they want to know exactly precise error and precise results, accurate results. Yes.
Because you are approximating the derivatives with high order, but you are not approximating the solution of the system. It's just...
No, what's here I'm using just the implicit scheme. It's not really, okay.
And it's because in using that discretization you will have, you will actually satisfy the condition that you have for the convergence of the algorithm.
Yes, yeah. Yeah, actually, there are some other ways to solve this obstacle problem. I think they are more or less equivalent. For example, the primal dual algorithm is exactly Howard, and I think we are facing, yeah, you don't have more than the superlinear convergence. And in this case, the best you get is the convergence with a bound NS which is independent of time. This is the best result I know. Okay, any other question? If not, now we have the last part, and in the last part, now we come back to the original problem. When we have both, we are minimizing and maximizing. What would you suggest for this problem? How would you solve it? Do you have any idea? So when we had just the minimum of the system, we did a splitting, like splitting. One step, you fix the policy and you solve the linear system. The other step, you fix the value and you minimize. You can try to do that in the same way. Two steps. One step, you minimize and maximize with the so you are given strategies, so you solve the system, and then the step after, you fix X and you minimize, maximize. You try to get, but this is, it doesn't work. It doesn't work because in this case, you can prove that your function, if you write this algorithm, it's not a Newton method, it's something else. And it doesn't converge. You can check it numerically in simple examples, just the example of two obstacles, for example, and you see that's where you are computing is far from the solution. So here it's you have to follow this this step. So you have a min max. So first you consider this first part, which is the minimization, whatever. You can minimize and then maximize, or maximize and then minimize. Here it doesn't matter. So first consider this operator for x and beta, and strategy beta, you consider this function where you have the minimum over alpha. And then your function g is the maximization of f beta x over beta. So you do it in two steps. And now the Howard algorithm is actually a nonlinear version, where first you do these steps like splitting. So you solve this nonlinear system, and then you improve the strategy. So first you are given the strategy beta, beta 0. For this strategy, at each step k, for this strategy beta k, you solve this problem completely. And then you improve beta by taking the argmax of beta, f beta xk. Here you fix xk. So this problem here is by itself, as we have seen before. It's a nonlinear equation, so you have to use the first Howard algorithm for this step first. And now this version, this nonlinear version, it's no more a Newton-like method. So you can try by yourself, try writing things. It's never like a Newton method. It doesn't have the same formulation. And of course, since you want to solve this problem by Howard algorithm, well, you know that you may have some errors, okay? Here, for example, I told you that we we solved the problem in a finite number because we had a finite number of actions. But if this set A has an infinite number of actions, then you know that you converge in a superlinear way, but you cannot guarantee that you have exactly your solution. So what you solve is with some error here. So what we ask to make the algorithm works is you have a set of sequence eta k, and you solve this equation, you solve this equation, xk, it should be less than eta k, okay? You want to have 0 here. Then you solve, you solve and you have xk less than eta k. Eta k being a positive sequence, and for the other step you do as before. Now, what you can prove is that if your sequence is finite, which means that you have eta k should goes to 0 when k goes to plus infinity, then the sequence you are computing, but this modified nonlinear Howard algorithm converges, and this converges to the unique solution of the min-max problem. And it is unique, again, because we are assuming the monotonicity of the matrices. This is what makes the solution unique. And we have some bounds on the solution. So, for example, we know that our sequence is converging towards xk, and it is like that. We have this bound, okay? So we know that xk is increasing, so xk is less than x star, but also we have this bound, so we have an error between xk and x, but not for the policy again. So this is all about the convergence of this vector x, error estimates, everything, but not for the policy, apart if you are in specific situations. So this is my final slide. This is just the example where you have two obstacles just to run in a very simple example, show that it works. So for example, if you have two obstacles in the obstacle from above, h, and this obstacle j, the solution is here. In this here we computed by PSOR algorithm. It's also, it's like a relaxation algorithm to solve the optimization problem behind. You remember I told you that if you have, let me show you. So if you are solving min-max qx minus bx minus g and x minus h is equal to 0, then the solution is related to the minimization of this quadratic form under the condition that x is bigger than g and lower than h. This is the optimization problem, and PSOR is like a relaxation method for this kind of quadratic problems. So if you solve it after 200 iterations, you get something like that. And actually, even if you increase the number of iteration, your solution is not very nice because of this behavior here. And this is what you get by Howard algorithm after 14 iterations. But be careful. In this 14 iteration, you are solving at each step, you are solving a linear system. So in total, you are solving 88 linear systems. But the solution after this 14 iterations, it's quite good. So this is just a simple example to compare with something else in the literature. And we are done. Thank you very much. Do you have questions or remarks?
Did you compare the times that last the two solutions?
Yeah. No, if you perform 14 iteration here and 200 iteration here, it's much more time here than for Howard. But you need a solver for the linear systems. Okay. Other comments or? Okay, so thank you very much and see you tomorrow. Okay, so just with the Claudia.